Now that we're going to start looking at extensive form games, I just want to revisit the notion of an extensive form and drill down into some of the details that we skipped over in Chapter 2. An extensive form is also called a game tree. A tree consists of nodes and branches. In graph theory, we talk about trees as being directed acyclic graphs, but we're not going to get into so much detail here. We'll just keep in mind that to define a game tree, we have these nodes and branches, and these graphs that we're going to draw have to have certain properties, and we'll go through those in a little bit of detail now. Given a node, let's call it x, there are going to be branches that come out of x. So if you have a branch from x to another node y, we say that y is x's immediate successor. If in turn there was further branches out of y, and one of those was to z, then we say z is also x's successor, but we don't call z x's immediate successor. The reverse relationship is that x is z's predecessor. X is also y's predecessor. In fact, x is y's immediate predecessor. X, however, is not z's immediate predecessor. Couple of things to note here. The successor relation and predecessor relation are transitive. So if x is y's predecessor and y is z's predecessor, then x is z's predecessor. Similarly, if y is x's successor and z is y's successor, then z is x's successor. A node that doesn't have any successors is what we call a terminal node. The node with no predecessors is called the initial node. Notice I use the definite article here because there can only be one initial node. And that's one of the first things we're going to note about a game tree. There is exactly one initial node. So that's the first point about a game tree. Now let me define for you the concept of a path. If we just go back here, let's suppose x were an initial node, then, and let's say z is a terminal node, then we can find a sequence of nodes, x, y, z, that leads us from the initial node to the terminal node z. And that's what we call a path. A path in a tree is a sequence of nodes that starts at the initial node and ends at a terminal node. Now, every path has to lead to a unique terminal node, and there has to be a path to every terminal node. In other words, there's a bijection from paths to terminal nodes. Why is that? That's because of the second important point about trees. Every node, except the initial node, remember the initial node has no predecessors, so every node other than the initial node has exactly one predecessor. If that's the case, if you follow two different paths, you're going to end up at different terminal nodes. Moreover, because every node has a predecessor, you can reach every terminal node from the initial node. So there's a path to every terminal node, and every path leads to a different terminal node. So what are we going to do with these trees? If you go back to Chapter 2, you'll remember that we label the nodes by the player who will be making the decision at that node, and we label the branches by the strategies or actions that the player has available to him at that node. So given that, at a given node, all the different strategies are different strategies. So all the branches have to have different labels. So that's our third point about a game tree. Because the branches are labeled by strategies, if there are two branches labeled by the same strategy, we don't know which branch you would go down if you follow that strategy. So each strategy gets one branch. And so the branches have to all have different labels. Now we also remember from Chapter 2 the idea of an information set. I'll remind you, an information set consists of nodes that a player can't distinguish between. Given that a player can't distinguish between the different nodes in an information set, we need certain properties to be satisfied for those nodes. The first one is that every node in the information set has to involve the same player. So the decision maker at all the nodes in a given information set has to be the same. If we have these two nodes, and these are in the same information set, but I'm the player here, I'm player 1, and you're the player 2, then of course, if I'm player 1, I can distinguish between these two nodes because I'm not the one making the decision here. Similarly, player 2 can distinguish between these two nodes because at this node, player 2 is not the one making the decision. So if in this information set we had different decision makers for the different nodes, then the decision makers would be able to tell the difference between those nodes. So all the nodes in a given information set have to have the same decision maker. Now, what would happen if I were to have the following scenario? There's these two different nodes that are in the same information set. So player 1 gets to choose between, let's say, A and B, and then player 2 can't observe what player 1 does. And so these two nodes are in the same information set for player 2. However, at this node, he gets to choose between X and Y, whereas at this node, he gets to choose between X, Y, and Z. Does this make any sense? No, because player 2 could obviously tell the difference between this node and this node, because if player 1 had played A and we ended up at this node, then player 2 would only have two choices. Whereas if player 1 had played B, player 2 would be at this node, and player 2 would have three choices. So by observing the strategies available to him, player 2 would be able to infer whether he's here or whether he's here. And that doesn't make any sense for us to then say that player 2 can't distinguish between those two. So that brings us to another property of a game tree, that every node in the given information set has to have the same number of immediate successors. So the number of strategies that a player could have at every node in the information set has to be the same. Moreover, the labels on them, the names of those strategies, have to be the same. So the number of immediate successors for every node in the information set has to be the same, and the labels of the branches that lead to those immediate successors have to be the same. And that's one more property of a game tree, or an extensive form. So now we've described several properties of these game forms. I'm going to give you one more thing to keep in mind. There's this idea of something called perfect recall. It says that players know what they have done in the past, so they can remember all the actions that they've taken. Let me show you a game. Suppose player 1 moves first, and then he gets to choose between left and right. And then player 1 gets to move again. He gets to choose between X and Y. Is it possible that these could be in the same information set? So this game tree satisfies all the conditions that we had stated earlier. But there's something messed up about this. Player 1 chooses between left and right, but then somehow we reach this information set here, and player 1 has now forgotten whether he played left or right. So he doesn't remember whether he's here or here, though he's the one who decided whether he went there or there. So perfect recall says that this can't happen. Perfect recall says that players can remember the actions that they've taken in the past. So that just says you cannot have... These information sets represent the information, like the name suggests. They represent the information that the players have. Based on what the information sets look like, there are broadly two classes of games. The first are what we call perfect information games. These are games where all the players can distinguish between all of the nodes, which means that all the information sets contain only one node. So in such a game, everyone knows the state of play at all times. So there's no hidden information of any sort. The second type of game is the complement of this set of games. They're called imperfect information games because there are going to be some information sets that contain more than one node. So in these types of games, there are going to be some situations where some of the players don't know some stuff. So because there might be some information sets which have more than one node, there are scenarios where a player may not know the exact state of play. So there may be hidden information. I say maybe because it's not necessarily true at all points in the game tree, but in some parts of the game tree, there would be hidden information. Before I continue, there's one more thing that I want to tell you about in terms of representing games as trees, and that has to do with when you have infinitely many strategies at a given decision node. Remember, we're going to label the branches out of a node by the strategies that a player has. So if you have a finite number of strategies, well, there's just a finite number of branches from the node. So there's a finite number of successors to the node. But what do you do when there are infinitely many such strategies? To take, for example, a duopoly game. You pick a quantity between some 0 and some upper bound, let's say q bar. Well, there's a continuum of strategies that you could choose from. How do we represent that? We can't draw infinitely many branches. What you do is you draw the lowest and the highest, and then you just draw an arc between them. So let me give you an example. So let's suppose firm 1 moves first. So we have a decision node for firm 1. We draw one branch for 0, we draw one branch for q bar, and we draw an arc between them. This just represents that 0 and q bar are possible strategies, and then there's just a continuum of branches between 0 and q bar. Instead of drawing a node for player 2 corresponding to each possible choice that player 1 might have made, we just draw one single node for player 2 in the middle, and we just draw, again, the strategies available to player 2. And if player 2 also has to pick a number between 0 and q bar, we would do the same thing, and then we'd write their payoffs. This is a case where player 2 observes player 1's choice and then decides what player 2 wants to do. If player 2 doesn't observe it, how do you draw an information set in this case? Well, we just draw a dashed line on the outside of the arc. So if we draw this dashed line on the outside of the arc, that represents that 2 doesn't observe 1's choice. So all of these different nodes, this continuum of nodes, are all in the same information set for player 2. We're now almost entirely equipped to start our analysis of these extensive form games. The only thing we need to remind ourselves about are what strategies are for these games. So let me give you another example of a game, and we'll go through writing down what the strategies are for each of the players. The example here is what we call the Ultimatum Game. This is a very commonly analyzed game in economics, and we see this applied to many different bargaining scenarios. It's a very simple bargaining game. Remember, strategies are complete contingent plans. So we've got a service that a seller will offer to a buyer. So player 1 is a seller, player 2 is a buyer. The cost of this service is 0. So there's no cost to the seller to providing the service. We're just going to make it 0 to keep life simple. The value is 100, and these are common knowledge. So we can write down the game where player 1 is going to set a price, P, and offer that to player 2. Player 2 can either accept it or reject it. If player 2 rejects it, then there's no transaction. Everybody gets a payoff of 0. If player 2 accepts it, then player 2 pays the price P that was set by the seller, and he gets to keep the surplus, the value to him, which is 100, minus the price that he pays, P. So let's write down that game. Player 1 chooses a number P between 0 and 100. Player 2 either accepts it or he rejects it. If he accepts it, he pays the price P to the seller. So the seller's revenue is P. Remember, the cost is 0. So the payoff to the seller is P. The value to player 2 is 100. So his surplus is 100 minus P. If he rejects it, then there's no transaction. Everybody gets a payoff of 0. Now, a strategy, remember, is a complete contingent plan. What is a complete contingent plan? We talked about this in chapter 2, that it tells us for every node where a player could be called to play, what should this player do? What are the nodes at which player 1 is called to play? Only the initial node. So all he has to do is pick a price. We just need to say what price he's going to set at that initial node. So his strategy space is just the interval 0 to 100. He has to pick some price between 0 and 100. Player 2, on the other hand, is called to play at all of these. So there's an entire continuum of nodes at which player 2 is called to play. There's one node here for every price that player 1 could have chosen. So a strategy needs to tell us, for each possible node that player 2 could be called to play at, what player 2 should do. So there's one node for each strategy that player 1 might have played. So a strategy for player 2 has to say, for each strategy that player 1 might have played, do you accept or do you reject? So let me give you one example of a strategy. You might have a cutoff strategy. And these come up a lot in economics. When we look for equilibria, we often find these strategies come up. So a cutoff strategy at price P lower bar is the strategy S2, such that given a price P, you accept if the price is less than or equal to P lower bar. That's your cutoff. But if the price exceeds the cutoff, then you reject. So that's one example of what a strategy might be. So now we're fully equipped to start looking at extensive form games. We know what game trees are. We know all the rules that govern what a game tree needs to look like. We know what strategies are. And so now we can start looking at the implications of rational behavior of the players involved in an extensive form game.